As we know, Sir Isaac Newton was an English mathematician, physicist, astronomer, natural philosopher, theologian, historian, and alchemist. I'm sorry if it's not enough. Our dear Newton is mostly known for the foundation of classical mechanics, for the invention of infinitesimal calculus, and for the theory of universal gravitation. You remember that story of the apple falling from the tree because it was attracted to the earth by a force that this gentleman called gravity? Wow, this is a very interesting story that I invite you to deepen because it's quite weird and somehow funny. However, today I wanted to call into question this important, if not fundamental genius, who lived between the 17th and 18th centuries for a very simple reason. Today we will talk about rheology, a very important science, very important in general, but also and especially for ceramic production. We will not focus, as we usually do, on a specific problem, but we will try to understand the important role that rheology plays, also looking closer at the main rheological behaviors of the suspensions used in ceramics. As usual, the challenge is to offer a short and easy overview, despite the topic is quite complex, today more than ever. I am Davide Trentini, and this is Apparently Invisible: Chemistry in Ceramics. Let's start with a definition. Rheology is the science that deals with the flow and the strain rate of matter. It's a branch of physics that studies the origin, the nature, and the characteristics of deformation of a matter under the influence of external forces, with particular regard to non-Newtonian liquids. And here is our Isaac Newton. I repeat it. Rheology is a branch of physics that studies the origin, the nature, and the characteristics of deformation of a matter under the influence of external forces. So, the keywords are deformation of a material in respect of an action that comes from an external force. Its main goal is to define the correlations between causes, that is, the forces, and effects, that is, deformations and flows, identifying all those mechanisms that are the basis of the different rheological behaviors on a microscopic and molecular scale. In ceramic industry, when it comes to rheology, we usually refer to the physical features of aqueous suspensions involved in the production process. But what suspensions are we talking about? The most significant are ceramic bodies, glazes, engobes, digital inks, and grid suspensions. To develop a good application, it is always important or even mandatory to check and adjust the rheological features of all suspensions. Just to make an example, the rheological study of ceramic bodies helps to provide the system with the proper stability, making the slurries easily manageable both during their transport within the plant and during their application. Well, this is a seemingly trivial example, but it tells us that the rheology of a suspension, after being analyzed, can be and often must be modified in order to get the right parameters that are requested for a proper application and therefore for a right development of the production process. This also tells us that the same identical suspension may require different type of rheological parameters according to the production parameters of each production line. That said, how do you study the rheology of ceramic suspensions? Ceramic suspensions are usually analyzed by means of specific tools called rheometers, able to collect all information about the flow of the fluid under examination. And I underline this word, flow. In ceramics, the most important rheological parameter are three, we could say. Viscosity, that is a measure of its resistance to deformation at a given rate. Then we have the flow limit, that is the value of the minimum force required to run a fluid, and we are talking about shear stress. And finally, the third parameter is the kind of rheological behavior that can be plastic, pseudoplastic, or Newtonian, and we will see them later. So, the keywords are viscosity, flow limit, and rheological behavior. The data that have been collected by rheometers are displayed on a two-dimensional Cartesian diagram, and while the vertical axis shows the shear stress, the horizontal axis expresses the velocity gradient, that is, a physical quantity related to the speed of the fluid. According to these data, the viscosity value is displayed on the diagram by the slope of the curve, and it is the result of the relation between the shear stress and the velocity gradient. The greater is the curve, the higher is the viscosity. And I stop here reminding you that if you want, you can download on our app the PDF of all episodes, just in case you want to collect and check whenever you want all the info. But that said, let's see now the most representative behaviors of ceramic suspensions, starting from the Newtonian behavior. The Newtonian behavior is a linear rate rheological behavior, and this means that the viscosity value remains constant even when the shear stress or the velocity gradient change. I give you a simple example just to be clear. Oil and water are the most significant example of this behavior. Both these liquids, in fact, do not change their viscosity value whether they are quickly or slowly stirred. Try to believe. We have all experienced what happens when we turn with a spoon in a glass of water. Nothing. And this is because of water's Newtonian behavior. In ceramics, instead, the Newtonian behavior is well represented by digital inks that must be Newtonian to be correctly applied by digital print heads. Why? Well, think about it. If the ink's rheological behavior were plastic or pseudoplastic, the piezoelectric impulse system that produced the ink drop would not be effective, leading to a lower printing definition or, at worst, preventing the formation of the ink drop. Print heads basically would not be able to spray and properly discharge the ink on the raw ceramic support. This finally means that the development of digital inks must take into consideration a rheological behavior that should be Newtonian. Let's now address the second of our rheological behaviors, speaking about the plastic behavior. The behavior of these fluids is marked by a specific flow limit, that is, a shear stress below which the fluid acts as a solid. What does that mean? It means that when the fluid is resting, it is very compact. But when it undergoes to a movement, the fluid softens, becoming more liquid. A typical example of this behavior is pastry cream. Instead, in ceramics, the most representative pseudoplastic fluids are slurries for ceramic body and grit suspensions. These two, in fact, must be able to keep the grit in suspension while they are resting, behaving, we could say, as a solid. On the other hand, during application, when a shear stress is applied, the suspension must show a sort of destructuring process, behaving as a pseudoplastic fluid. That means that the viscosity decreases while the velocity gradient gradually increases. Here's another clear example, just to clarify. During the application by means of spray systems, the fluid, that is, the grit suspension in this case, undergoes to a very high speed, thus leading to a very low viscosity value and therefore allowing a proper nebulization. And to reach this rheological behavior, it is important to use the specific chemicals able to provide the suspension with a suspending action that ensures the flow limit, a binding action that provides the system with cohesion and homogeneity, and a little of pseudoplasticity. Without these chemicals, the mixture would easily show sedimentation phenomena, just like sand in water, of course compromising the application. And what about slurries for ceramic bodies? In this case, it is important to highlight that all clays, by their very nature, are marked by a strong plastic behavior. And this is the reason why these suspensions require chemicals able to drastically decrease or even remove both the flow limit and the very high viscosity, turning the jelly system into a fluid system. And now let's go on with the third rheological behavior, that is the pseudoplastic behavior, that is marked by a decrease in viscosity with an increase of the shear stress or the velocity gradient. Some might say, okay, is the same of the plastic behavior? Yes, but with a very important difference. Unlike the plastic behavior, in this case there is no flow limit, and so there is a lack of initial force that put in motion the fluid. What does that mean? In very, very, very simple words, it means that due to the lack of flow limit, the fluid behaves as a liquid even when resting, and it needs a very little effort, almost zero, to move. A typical and very clear example of this category of fluid are the self-leveling resins for floor application. Think about it. When they are discharged on the floor, they do not need any movement, that is, any shear stress by the operator. They do everything by themselves. This is very enlightening, I think. But going back to ceramic production, we can surely say that all glazes for eyeless applications can be considered as part of this group, pseudoplastic. These glazes are nothing but water suspensions of extremely fine vitreous particles. The chemical and physical features of the particle, as well as their size, mean that these systems almost do not require a flow limit, since the sedimentation during the resting phase is very slow, and the lack of flow limit usually ensures a good and proper leveling during application. So, the rheological curves of pseudoplastic and plastic fluids are actually very similar, but, as we said, with an important difference, the lack of flow limit. Good. Let's now end our overview with the fourth and last behavior, the dilating behavior. These fluids usually increase their viscosity with the increase of the velocity gradient. We could consider this behavior as the opposite of the plastic behavior. And in ceramics, dilating behaviors are unusual, and they are basically avoided since they are not suitable for any ceramic production processes. For example, since the viscosity value increases as the speed gets faster, a spray application could be very difficult or even impossible. So, we are saying that the fluids marked by a dilating behavior may lead to problems during an application, also negatively affecting a good technical or aesthetic result. And to be better understand a dilating behavior, I just want to end the episode with this last example, that giving a look at the world of motorcycling or extreme sports. Today are available on the market protective suits made with materials marked by dilating technical features. They are basically soft, allowing the person who is wearing the jacket, for example, to easily move. But in case of an impact that develops an increase of the movement speed, they immediately harden, protecting from possible contusions or damage. And with the dilating behavior and motorcycling, we end here our review on the main rheological behaviors. Of course, you can write us for more information as usual. I remind you that you can listen to the previous episodes on the main platforms or on our app that you can download for free on Apple Store or Google Play by typing Z and S Ceramco or Apparently Invisible. At this point, I just have to say goodbye, and while I'm eating an apple in honor of Isaac, I just say, see you soon.